Hello everyone, my name is Sriram Sankar and I support teams that work on the silicon lifecycle for our custom silicon at Meta. One of our key responsibilities is to deliver reliable silicon that powers all of our AI applications. My colleague Harish Dixit will join us soon and talk to us about silicon reliability. Today, we are going to talk about why AI hardware reliability matters to us at our scale. Meta supports a lot of different customer use cases across our services: Facebook, Messenger, Instagram, and WhatsApp. It has billions of video encodings on Reels, and our open source Llama model had 1 plus billion downloads recently. On the AI arena, we have moved from text to image generation, large language models, and AI enabled creation tools for our customer worldwide. We have a significant amount of infrastructure that is distributed globally to support this AI enabled landscape. Our data centers are distributed across US, EMEA, and APAC regions. These are large buildings that can support hundreds of thousands to millions of servers. And they also are integrated across our backend and network fabric. When it comes to server infrastructure, we have a long history of contributing to Open Compute project. Starting all the way from 2011, we have contributed compute solutions, storage solutions, and AI solutions. And all of these are open source. Designs are available at Open Compute project. The data centers, servers, and all infrastructure within have to come together to deliver our AI services. This includes the GPUs, the server, the rack, the network behind them, and the services on our infrastructure stack, like storage, compute services, that have to work together to provide training clusters at scale. When we build large clusters like this, we know from our experience that hardware eventually fails. An hardware issue or an hardware failure is something that we cannot get away from. So today, we are going to talk about hardware failures at scale. We are going to pick apart the different hardware failures that we see in our infrastructure. We are going to focus on one particular type of them, silent data corruptions, and why that matters. We're going to talk about how we solved some of these challenges at our scale. How did we scale to meeting the reliability requirements of our AI applications? And finally, a call to the industry on how we can incorporate factory to fleet techniques to encounter this challenge in the future. When we talk about hardware failures in an AI cluster, there is a lot of different things that could fail. Broadly, the hardware itself could fail due to manufacturing, due to physics of the hardware, whether it's a memory, whether it's a GPU, whether it's the network devices. Then the complexity of the network that interconnects them is also a big deal for us in our AI hardware. And also our configuration for software could also be causing a lot of issues. Across these board, one key thing is that 66% or more of our training job interruptions are caused due to hardware failures. When we look at larger and larger clusters, this problem is only going to get worse. When we move from small clusters, 2K, 4K, to 50K to 100K clusters, the interruptions that we get per hour increases significantly higher. More accelerators means more failures for us to handle. Hardware failures themselves are of different kinds. There are some errors that are hard failures. They are static in nature. If they fail, they don't get back up again. So these are easy to detect. You just go check for it, and if the hardware doesn't come back again, they are static errors. There are some errors that happen during the course of a workload run, and they are transient in nature. They are intermittent. You need detection mechanisms to detect them in a fleet of our scale. There is another category of errors that are way more insidious in nature. We call them silent errors because they do not have any kind of record that an error has actually happened from the hardware all the way up to the stack. These are extremely hard to detect, diagnose, and mitigate in our fleet. And I'm going to hand off to Harish to talk about them in more detail.
Thank you, Sriram. I'm really excited to talk about silent errors. So what are silent errors? Let's consider a computation such as 2 plus 2. We all know that it's supposed to compute to 4. So when we say something is a silent error, we're fundamentally seeing a scenario where 2 plus 2 computes to 5. This is something that you typically don't expect a calculator or a computer to do. So what's happening here? What's the characteristics of us in observing these kinds of faults? So we classify these kind of errors as silent errors, as Sriram was highlighting earlier. So fundamentally, these are defects in silicon. And when you have a computation such as this, there is typically no residue that is available in the system to say that this kind of a miscomputation happened. So inherently, these are really hard to detect. And as you can imagine, since there is no detection or detection is really hard, these can stay dormant for months, if not years. And a service which is consistently doing the computations will keep consuming these incorrect values and then will keep making incorrect decisions. And as a result, you will start noticing a scenario where a service has consumed enough of these incorrect values, and this results in a significant impact to services. So you might say, hey, I've heard this story before. There was this story around cosmic rays randomly hitting this particular transistor at this particular point of time, and you happen to have the right conditions, and you would see a bit flip. But what we are specifically talking about here is something that is a larger order of magnitude than what we typically observe with cosmic rays. So if we looked at some of the studies in early 2000s, cosmic ray induced faults typically were manifesting at one fault in a million devices. Initially, there were reports around this being a bit of a higher rate, but a lot of the community came together and they started this work stream around software research, and we were able to bring it down to one fault in a million devices. So when we talk about silent data corruptions, we are fundamentally talking about defects in silicon. And we are observing that these faults occur at a rate which is 3 orders of magnitude higher than what we have previously noticed with cosmic rays. So one fault in 1,000 devices, when there are millions of devices which are operating at scale, is a huge problem. And as you can see by this animation that's going around, on the left side, you can hardly see any red dots. The red dots representing the faults, of course. And on the right, we see that these red dots are bouncing around, and that's the number of corruptions your hardware is seeing on an annual basis. And this is a really hard problem for us to guarantee reliable infrastructure. So let's understand why this is a hard problem. What are some of the parameters and characteristics which make this a hard problem? So when you're dealing with silent data corruptions, you might say, hey, it's just a set of computations. I have very powerful CPUs and GPUs. I'll just run through all these computations and verify that all of those computations are correct. What we have noticed, and this comes through 7 years of observation around this problem, is these errors are inherently dependent on data randomization. For example, let's say you're doing 3 times 5 as a computation. You're getting 15, which is the correct answer. But let's say you do 3 times 4. You're supposed to get 12, but you get 11. So that inherently means the corruption only manifests for a certain subset of values instead of manifesting for all values. So you never know where you're going to get a corruption unless you happen to exercise that set of values, which makes it really hard for us to scale through the test space. The test space immediately becomes infinite. The other parameter that is associated with silent data corruptions is that these are fundamentally dependent on electrical properties associated with silicon. For example, characteristics like frequency, voltage, and current tend to have a huge impact in our ability to be able to reproduce these issues. You might have the correct answers at one voltage and frequency, whereas at a different voltage and frequency, you may get an incorrect answer. So given our scale, since our data centers are placed in a variety of geolocations and also run at varieties of environmental conditions and temperatures, we also are able to observe weak correlations of these data corruptions being dependent on temperature. And as a result, some of these computations will be fine at certain temperatures, and the same computations will then be incorrect at some other temperatures. And to add to all of this challenge, we also notice life cycle variations. So what that means is, let's say you're verifying all of your chips today to say, these are great, they are all providing correct answers. But maybe 6 months down the line, the same chip which provided the same answer, which was correct, will give you the incorrect answer. We actually did a specific case study around this particular scenario where we asked one of the devices to do the same computation over and over again. And after 6 months, it failed for the same set of computations it was passing for before. And as you can see, if we were to contrast this with hard and transient faults, In hard and transient faults, the telemetry is available. You can detect it, as Sriram highlighted earlier in the presentation. But when you have this characteristic that is associated with silent data corruptions, you're left with no other choice but to test your fleet continuously and for a variety of random configurations and values. And that's where we start getting into the scale of the problem, right? So you have these millions and millions of servers. I'm talking about data corruptions, maybe a set of values on certain set of sub-servers and certain set of electrical properties. But how did we scale our approaches? How did we go from saying, hey, this is a one random SDC to hundreds or thousands of SDCs? And you remember, I just previously mentioned around, hey, we have to continuously test through the fleet. So that's basically the first approach that we tried. We said, let's put our infrastructure through pit stops. In a Formula One race, the drivers typically take a pit stop to refuel, to check over the maintenance operations. Similarly, a large-scale infrastructure goes through non-production states. And in those states, we have the opportunity to piggyback on them and run directed tests. And sometimes it's in the order of minutes. And when we do this, and the fleet is consistently cycling through these stages, we are able to cover the entire fleet in over a month and a half. And when we consistently started running these tests, what we observed was over 70 to 80% of the data corruptions that we were able to observe in our services were also being detected by our mechanisms. But as you can imagine, if I have corruptions, and if I tell someone, hey, I know this corruption signature, but you have to wait 45 days before I can guarantee whether you can run your application or not, it's actually not something that we can live with. So this is too slow across a live fleet. So we need a creative approach, which is a lot faster, maybe gives us a bit more partial coverage. And that's where the next framework comes through. We call this ripple, and as the name itself suggests, this ripples through the infrastructure without leaving a larger footprint on the workloads that are running. So this approach co-locates with the workload. Think of these as in-production tiny tests, where the test time is in the order of milliseconds. The workloads don't notice any performance impact. There's a scheduler which is intelligently scheduling all of this behind the scenes. And if we have this approach correctly configured, which we do, the time to cover the entire fleet reduces to 7 days. And using this approach as well, we've been able to detect even more novel data corruptions. And what we've observed is both of these methods provide unique coverage metrics among the defect space. So while these are testing approaches, our infrastructure is spending some cycles rather, to run some of these tests and stay away from production while we are running these tests, or manage the impact of these test mechanisms while the tests are running in production. What if we could detect corruptions by using the power of large-scale analytics, as well as all of this study that we have done by consistently running tests on all these devices? And that's where our next approach comes through. We call it hardware sentiment. This is a paper from ASPLOS 2025 this year as well. So using this approach, what we are attempting is to move to a test-free methodology towards SDC detection. And what do I mean by that? So imagine a fleet of millions of servers. There are all these random applications which are now scheduled across all of our fleet. But it just so happens that some applications are always failing on certain subset of cores with a certain trace. And if you start noticing this frequently enough, you'll be able to triage a particular set of hardware devices with a particular set of cores, which always end up causing some problem to the application, which may not be obvious to the application or to the hardware, but for the keen observer, these tend to show up. And when we started aggregating all of these, we categorized all of the failures associated with this mechanism, did a root cause, were able to confirm our approaches with some other data corruption tests, and we were able to identify that, hey, this application-based methodology, which doesn't even run tests, performs 41% better than the methodologies that we have which run tests. So far, we've looked at how testing-based approaches as well as analytical approaches are useful in detecting data corruption. But how do these data corruptions fundamentally affect AI workloads? So we can classify AI workloads into two different categories, the first one being training and the second being inference. Very specifically, with training algorithms, data corruptions typically affect the gradient descent algorithm. So if you have a corruption, the gradient computations as well as the weight propagation could potentially be incorrect. And when that happens, you think the training job is making forward progress, but in reality, it is not. There is another type of corruption where the corruption is beyond the value representation that is possible within floating point numerics. And this is where typically a computational value gets represented as not a number. So when this happens, this not a number representation starts propagating throughout the entire training job. And as a result, the training job is again not making forward progress. And this is a really hard problem when dealing with large-scale clusters with thousands and thousands of devices. And as a result, in addition to the approaches that we discussed before, we also have some software handshake approaches such as algorithmic fault tolerance, detection of NaN within PyTorch, as well as periodic detections. In addition, within inference workloads, the corruptions manifest in very interesting ways. You might say, hey, instead of showing a picture of a dog, I'm showing a picture of a cat. Why does that matter? But very specifically with inference workloads, these corruptions end up in second-order effects. For example, a privacy configuration is incorrect, or an integrity configuration is incorrect, or a recommendation configuration is incorrect. And as a result, because of these second-order effects, we still want to mitigate corruptions within inference stack. So specifically for inference, we have identified which layers are a lot more sensitive to corruptions in comparison to some other layers. And this methodology, we call it as parameter vulnerability factor. And in addition to this, we also have an approach called as Dr. DNA, which identifies when inferences are diverging from their expected values at scale. The curious reader can find more about all of these techniques in our blog. With that, I'll hand it off to Sriram to summarize the journey of silent data corruptions at scale.
Thank you, Harish, for walking us through why silent data corruptions are such a hard problem and how that impacts AI reliability at our scale. We have handled silent data corruptions within Meta, but we have not stopped there. We have driven this as an industry-wide problem from when we started seeing the data corruptions to when we first published our landmark paper in 2021. We have continued to push academia and industry to find a common solution for this problem. In 2022, we had an RFP and academic collaborations that we kickstarted. In 2023, we worked with OCP across multiple hyperscalers and semiconductor manufacturers to create a work stream to tackle this tough challenge. And in 2024, we have the joint RFP with OCP to tackle this challenge at scale. This has been a journey, but this is important for the industry to solve. However, are we doing enough? We have detected what we could. We have detected errors where it was extremely hard to do so, going down to the depth of the silicon. But we have a lot more that is left unknown and undetected. So what do we do? This is not an easy silver bullet or an easy solution to this problem. We need to look across the life cycle. We need to look at everything from the factory all the way to the fleet, and we need to look at everything all the way from the silicon to the application layer. We need to find a solution that spans both horizontally and vertically. When we look at factory to fleet, there are different areas and different domains where we need to improve our quality and our design. Design and architecture needs to consider RAS capabilities at the beginning. We need to incorporate debug hooks and telemetry in implementation, and we need to validate and verify this when we build post-silicon. It doesn't stop there though. In labs, at the integration site, and in manufacturer, we need to look at yield, manufacturing approaches, and diagnostics to tackle this problem. And when you deploy it in the fleet, we need to use that diagnostics. We need to look at firmware configs and silicon improvements. We need to look at analytics that comes out of the fleet and look at monitoring across the life cycle. When it comes to the stack, we need to look at all the way from the chip, but we need to be very closely tied to the board and what telemetry it could provide. We need to look at how the server is deployed and provisioned. We need to look at our kernels, the OS layer, and figure out what we need to put into our infrastructure and work with our compiler and AI workloads closely to handle hardware failures at our scale. For AI workloads, that is even more critical as we see more and more complex behavior at scale. We are working on our own custom silicon. We call it Meta Training and Inference Accelerator, MTIA, where we are working on best-in-class technologies. We are shipping at the speed of light, and we are delivering industry-leading reliability. We have multiple iterations of this already in production, and we are working on future chips as well. Remember that hardware faults dominate the cluster reliability challenges that we face. And as we saw, the complexity of the faults increases exponentially, both the nature of them and how they appear at scale. Across the industry, we need a factory to fleet approach where we improve every stage of the process, and we need integration all the way from the chip to the application level. For our silicon, reliability is a first-class design consideration, and Meta is delivering foundational changes to this space. Thank you for listening to the talk and hope you enjoyed it.